Welcome students. In the last lecture, we had some discussion on the RF link or the radio link in between the satellite and the ground station. So in our previous lecture, what we had done, we had seen the power spectral density, the power flux density. It's not power spectral density, rather the power flux density. And we had seen the power flux density, that is the transmitted power by the transmitter with respect to this, the area of the sphere, assuming the antenna is radiating power in all the directions. So in a spherical manner, the power is radiated. So we calculated the power flux density is transmitted power divided by the area of the sphere. And if we take two different points, suppose this is the point or the source point from which some amount of power PT is generated. Now consider this is a sphere, and this sphere is having a radius RA, and you have some another sphere which is having some different radius, that we can take it as RB. If I calculate the power flux density for a sphere of radius RA, then we can write that transmitted power divided by 4 pi into RA square. If I calculate the power flux density within a sphere of radius RB, that is the transmitted power divided by 4 pi RB square. And after that, if you want to make, or if you want to establish a relationship in both of the power flux density at a radius RA and power flux density at radius RB, then we can write it as RB square divided by RA square. Okay, so this implies the power flux density is inversely proportional to the radius or to the distance at which the radio wave travels. And then we discuss an important parameter that is called EIRP. So EIRP stands for effective isotropic radiated power, because we have assumed the power which is radiated by the transmitter, it is equally throughout all the direction. So that is why we have taken the term that is isotropic. So isotropic means the power is radiated in all the direction. In the 360-degree direction, power is radiated. So EIRP can be defined as the PT multiplied by GT, where PT is the transmitted power and GT is the transmitter antenna gain. Now, if we take the logarithmic, that is log base 10 of EIRP, so this we represent by capital EIRP. So this is in dB. So when we calculate in logarithmic scale, so that means we have to take 10 log base 10. So it will give us that we represent by capital EIRP in dB. So this equals 10 log base 10 into PT into GT. So this we can write 10 log of PT plus 10 log of GT. So that equals this we can write as PT plus this we can write as GT. Or the summation of the transmitted power. So this transmitted power is in dB, and the transmitter antenna again that is also calculated in dB, because I have taken the logarithmic in both of the cases. Okay, now if I consider the same power flux density, if I consider the same power flux density at a distance r, so power flux density at a distance r, I can write that is equal to the transmitted power into, if you see in the previous case, we have explained the power flux density in terms of transmitted power divided by the area of the sphere. Okay, but now what we are going to do, the transmitted power is not only dependent on the PT, it is also dependent on antenna gain, that is GT. So correcting the power flux density expression, we can write it as PTGT divided by 4 pi r square. The unit will be in watt per meter square, because watt is the unit of power, meter square is the unit of area. But my point that we can write, since we know this PT small gt is EIRP in small EIRP, that is equal to 4 pi r square. Now, if I will take the logarithmic from left hand side and right hand side, so this will be log base 10 of power flux density at a distance r. This equals log base 10 log base 10 EIRP divided by 4 pi r square. All right. So this thing, when I took logarithmic, let me express this as the capital power flux density at a distance r. So this will be in unit of dB, because I'm taking the logarithmic, so it will be in unit of dB. So this, now this expression we can write 10 logarithmic of base 10 of EIRP minus 10 logarithmic of base 10 4 pi r square. If you recall, this thing we have represented by capital EIRP. So this is in dB. All right. Now minus this particular term, I can represent 10 log base 10 of 4 pi minus 10 log base 10 of r square. And hence this one EIRP in dB minus 10 log base 10 of 4 pi. 4 pi is a constant here, minus it is r square. This 2 can be multiplied with this 10. So I can write 20 log base 10 of R. So if you take pi, if you put the value of pi 3.141 and if you multiply with 4, you will have some 12 point something. And if you take the logarithmic, so it will come as around, this result will come as around 11. So I can write here as E I R P in dB minus this value will be 11 minus 20 log base 10 into R. Okay, so now if you observe the calculation of power flux density at a distance r in terms of dB, when we calculated, we got it as a function of the IRP as well as the radius or the distance at which we are calculating. So as the distance increasing, this particular factor, it will gradually decrease. So power flux density is inversely proportional to the distance. All right. Now, if we focus on the antenna gain or gain of antenna, normally if you take an ideal antenna, so the gain of an ideal antenna is equal to 4 pi a divided by lambda square. Here a is the aperture area of the antenna. Okay, so A stands for aperture area of antenna. But if you think in a realistic way, then your antenna, when the power falls on the antenna, some of the power will be radiated out of the antenna. Some of the powers will be absorbed by the lossy components. So there are some amount of power which only will be absorbed by the antenna. Not all the power which is falling on the antenna will be absorbed or will be received by the antenna. Few amount of the powers which will be observed or received by the antenna. So we denoted a term that is called antenna efficiency. So antenna efficiency tells what is the effective aperture of the antenna divided by the ideal or the total aperture area of the antenna. So that is the antenna efficiency. Hence, we can here also write the value of A, that is equal to AE divided by eta. Or else we can write AE is equal to eta into A. Okay. So where AE is the effective aperture of the antenna. So effective aperture represents what is the real or what is the physical antenna size which is actually accepting the power. It's not the all the size which is accepting. Some portions of the antenna, they are radiating the power. There are some lossy components which in the antenna which is accepting the power, but few portions of the antenna which is only accepting the power. So that we call as the effective aperture. So we can write what is the real antenna gain. So real antenna gain is nothing but 4 pi AE divided by lambda square. Now using this value of A here, we can write 4 pi A is equal to eta into A. So eta into A divided by lambda square. So this represents the real antenna gain. So if we have this expression, G real is equal to antenna gain multiplied by 4 pi a divided by lambda square. So this expression represents if a given antenna size is physical size is given, that is a, and the wavelength at which the signal is transmitted, received by the antenna is given, and of the antenna is known to us, out what will be the gain of the antenna. So that implies the gain of the antenna is inversely proportional to the square of the wavelength, or that is antenna is directly proportional because lambda is equal to c by f, so it will be directly proportional to the frequency. A signal, and the signal is I'm transmitting it at a very high frequency, then the gain of the antenna will be higher. Okay. Now let us take an example. Suppose I have a parabolic antenna. Okay. Let me draw the shape of that. Suppose this is the antenna. Okay. So this is the parabolic antenna. And let me assume the diameter of this aperture. This diameter aperture is small d. So what is the area, or what is the physical area? Physical area is equal to pi d square divided by 4. So what this represents? It represents the area of this circle. But if you remember previously, we have calculated the area of a sphere. So when we calculate the area of a sphere, that value is equal to 4 pi r square. If you recall here, yeah, if you see here, we have represented the area, that is 4 pi r square. So this area is nothing but area of the sphere, because if I have a transmitter, here I have an antenna. This antenna is transmitting power towards up, towards right, towards left, towards down, towards my side, towards your side. That means in a sphere, the power is radiated. It is not radiating in a particular direction. So that's why this particular term 4 pi r square, it represents the area of the sphere. So here we have considered my antenna, which is a parabolic reflector antenna. So this area represents area of this surface, or this particular circle. Okay. So area of the circle is pi r square. So if you put d is equal to 2r, so it will be 4r square. So 4 will cancel, it will be pi r square. Correct. Now let us calculate what will be the gain, or gain of this antenna. What is the gain of real gain of the antenna is equal to eta into what we have done, eta into 4 pi a divided by lambda square. Am I correct? Okay. So that equals eta into 4 pi divided by lambda square. This a is what? It is the physical area which we have represented here. The physical area of the antenna, that is equal to pi d square divided by 4. All right. Now, here you have a 4. Here you have a 4. Both will cancel each other. So what you will have, eta into pi d divided by lambda whole square. So this is the real gain of a antenna or the real gain of my antenna, which is having a diameter d. All right. Now here we know that lambda is equal to c divided by a. So here I can write eta into pi divided by c into f d whole square. So this particular term pi divided by c, it's a constant because pi value is known, c is the speed of light. So this is a constant. So that means the gain or the gain of the antenna is directly proportional to the frequency and or the square of the frequency, rather it will be correct to say square of the frequency and directly proportional to the square of diameter of the antenna. That means if you take an antenna of larger diameter, then it will have a higher gain. And if you take, if your operating frequency is higher, then also it will have higher gain. Now, if we will calculate the gain in dB, so we have to take the logarithmic, so 10 log base 10 into eta into pi by c square f square d square. I'm writing from this equation. Okay. So this we can write, it's a constant. So 10 log base 10 into pi by c square plus 10 log base 10 eta. Again, eta is a constant because if antenna, this is the gain, sorry, efficiency of the antenna. So that will also be given. If but for a particular antenna, this value will be given plus 10 log base 10 f square plus 10 log base 10 d square. Okay, so this also I can write in this pen. Here it will be square, so I can write it as 20 log base 10 pi by c plus 10 log base 10 of eta plus 20 log base 10 of f plus 20 log base 10 of d. So this expression again tells us that if you want to find the gain in dB, so that is also proportional to the frequency and the diameter of the antenna. Got my point? Now, we also have discussed beam width of the antenna. Okay, if you recall, beam width. So what we have seen normally, if there is an antenna, this is assume that this is the source or this is the antenna which is radiating a beam of signal. So that beam will be radiated in this direction, whereas you will have some minor lobes. Okay, so these are called as the side lobes. This is called the main lobe, where this direction is called the bore side. This direction is called the bore side. Okay, and this angle is called the beam width of this antenna. So this angle can be represented by theta is equal to 75 multiplied by lambda divided by d. So from this, we know that this theta is directly proportional to lambda and inversely proportional to 1 by d. So directly proportional to lambda means we can write theta is inversely proportional to frequency, because lambda is equal to c by f, so it is inversely proportional to frequency. So what we have come across here, if we will take an antenna which is having a large diameter, then what happens? The theta will be lesser. That means diameter. And if we'll take a large frequency, then theta will also be less. Okay, so if you want to transmit in a particular direction, if the antenna want to transmit in a particular direction, then we have to consider a larger antenna which is having large diameter and higher frequency, so that the antenna can transmit in a particular direction. But if you want to receive in multiple direction, that means if this is your antenna and somewhere the satellite is here, if you want to get the signal from the satellite in this direction, then the antenna should have a larger beam width. Okay, larger beam width means the antenna can transmit in this direction, this direction, this direction, this direction. Larger direction the antenna can transmit. So wherever is the location of the satellite, here or here or here or wherever the satellite is, the antenna can transmit. Because the antenna which is located at the ground station, you cannot rotate the antenna. Your satellite is moving in this way, so you cannot rotate. Okay, so it will be better to choose a satellite as to choose an antenna which will have the larger beam width. So to make the beam width larger as possible, let us decide then what will happen. If you want the value of theta to be high, then d should be, diameter should be low or diameter should be small. So that is the reason nowadays if you see our DTH antennas, the size is being reduced. So the size reduces in the sense it will have a larger beam width. Okay, so if, because as we also have discussed that although we are telling that geostationary satellites, they are locating at a particular position, but it is not practically possible. There are many factors which are responsible. Factors like the satellite which is moving. It is moving in some atmosphere. There will be some friction. Air is there, and friction will happen. So due to that friction, the satellite position may differ. Next thing, our Earth is not a pure sphere. Okay, so many things are responsible for the diversion of the satellite point. If we have a larger beam width, then we can get the signal or transmit the signal to the satellite. So that is the reason why our DTS antennas are having smaller size. So smaller size means the beam width will be larger. Okay, so this is what we had discussed before. Now we are going to discuss today free space path loss. Okay, so what we have seen now, if you recall, what is the amount of power received by any receiver? This power received by suppose I have a receiver antenna, how much power I will receive? So this received power is directly proportional to the transmitted power. Is it or not? If the antenna is transmitting, if the transmitter is transmitting high power, then the receiver will receive high power. Correct. And it also directly proportional to the effective aperture of the antenna. That means if your antenna will have a large effective area, uh, where I have shown uh, so anyway, if your antenna will have a large effective area, then it will collect more power. Okay, so that means what? When a transmitter is transmitting, this is the transmitter, this is the receiver. When the transmitter is transmitting power, it is transmitting in all the directions. The power is transmitted, but a receiver is somewhere here. So how much power the receiver will receive? If the transmitter is transmitting PT power, does the receiver receive PT power? The answer is no, no, never it will receive PT power. How much power? It will receive what is the power flux density. That means what is the amount of power per unit area. What is the amount of power per unit area at a some distance multiplied by the area of the receiver. So that is the power received. Let me write here the power per unit area. Okay, because it is radiating in all the direction. So power per area multiplied by area of receiver or the receiver area. That is the amount of power the receiver will receive. So this power per area, this is called this factor is called power flux density. So we can express the received power PR, that is equal to power flux density multiplied by the effective aperture of the receiver. So that implies what is power flux density? We have studied the power flux density is PT into divided by 4 pi r square. 4 pi r square is the area, is the total area of the sphere. The, the total power, the power area of the sphere that gives the power flux density multiplied by AE. And AE, we know what is the value of AE? That is the effective aperture. So it is equal to eta into what we have done here. Just recall. We are calculating AE. A is here. Eta into A. Okay, this thing we'll use. Eta into A. A is the physical aperture. It is not the effective aperture. A stands for the physical aperture. So this equals eta into PT TT divided by 4 pi r square. Okay, and then we have A. A is the physical aperture. So what is the value of A here? If you take where this one, A is equal to pi d square divided by 4. is into pi d square divided by 4. All right. Is it clear? Okay. So this one, this power, received power, PR, we can write PT divided by 4 pi r square into what is the effective aperture we have represented? Effective aperture of the antenna, where effective aperture, this one, AE is equal to eta into A, and A is what? A is the physical aperture. So what we can write in place of A? Got my point? That means, for example, I will what I will write here. Suppose I am writing the side. What we know that gain of the antenna is equal to 4 pi AE divided by lambda square. This much, this thing we have studied or not? So here, what is AE? What is AE? AE is equal to G into lambda square divided by 4 pi. We can write by doing cross multiplication. I am writing this. So this is what this AE. So we know the power flux density, this thing, multiplied by AE value G into lambda square divided by 4 pi. So what do you mean by G? G is the gain of antenna. Gain of which antenna? Transmitter or receiver antenna? It is receiver antenna. Why? Why I'm telling receiver of antenna? Because when I said we are calculating the power received, okay, so it is the power flux density. So power flux density, it is the depends on the transmitted power, means how much power is transmitted per unit area by the transmitter. That is the power flux density multiplied by AE. So AE is the effective aperture. Effective aperture of whom? Transmitter or receiver? It is the receiver. Okay, so I have shown in this diagram here what is the aperture, effective aperture of this antenna. If it will have more aperture, it will receive more power. If it will have less aperture, it will receive less power. So this aperture AE is for receiver. So this gain we have represented AE in terms of G lambda square. So this gain is for receiver antenna gain. Got the point? So this gain is nothing but the gain of the receiving antenna. So this we write in this particular manner that PT dt divided by 4 pi r square. So this is the power flux density multiplied by gr multiplied by lambda square divided by 4 pi. Okay, so this term is called spreading loss. Got the point? So this is called spreading loss. That means if or this spreading loss is represented by a torque S that is equal to lambda square divided by this is S so that means if frequency, then we will have what? Less spreading loss. Now from this, if you want to calculate what is the free space loss, so I can write this PR. I'm writing this equation. I'm writing this equation again. So PR is equal to PT GT. So PT GT GR. Okay, I have multiplied this GR. Now you see here this divided by, in the numerator you will have lambda square and here 4 pi square into r square. Is it correct? So this I can write PT GT GR, where PT is the transmitted power, GT is the gain of the transmitter antenna, GR is the gain of the receiving antenna, divided by 4 4 pi r by lambda square. Are you agree? Any mistake we have done here? Oh, correct, correct. We have 4 here. There are 2 4s, this 4 and this 4. Okay, so it will be, so 4 pi r square of this. Okay, so this amount, that is 4 pi r by lambda square, this is called free space path loss. So which is represented by L Fs. So L Fs is equal to 4 pi r by lambda square. So this is called free space path loss. Now, if you have to calculate the free space path loss in dB, okay, so then we can take 10 log base 10 4 pi r by lambda square. So that is equal to 20 log base 10 4 pi r divided by lambda. So again I am writing 20 log base 10 4 pi. If I write lambda is equal to c by f, then it will be divided by c into f into r. So this equals 20 log base 10 4 pi by c, because 4 pi by c is a constant, plus 20 log base 10 f plus 20 log base 10 r. So that implies the path loss or the free space path loss increases with increase in frequency and increase in the distance. That means if we are using a frequency which is high frequency, then the path loss will be higher. Path loss means the difference between the power which is transmitted by the transmitter and received by the receiver. So that difference is called path loss. Means what is the power transmitted by the transmitter and what is the power received by the receiver. Okay, so that is called the path loss. So path loss, if you see LFS, it is directly proportional to frequency as well as the distance. R is the distance of separation between transmitter and the receiver. Okay, so with this we have completed the free space path loss, and I will share the note of this section. If you have any question, then we can discuss.